A uniform rod of length 2 meters and weight W is freely hinged at a point P. The rod of relative density 0.756 is free to move about a horizontal axis through P. The other end of the rod is immersed in a liquid of relative density 0.9. By the way, the horizontal axis through P is coming out of the screen or into the screen, perpendicular to the plane of the screen. The point P is 0.4 meters above the surface of the liquid. The rod is in equilibrium and is inclined at an angle of theta to the vertical. We want to find the length of the immersed part of the rod. We are obviously dealing with an extended object here, not a particle. So the weight vector can be shown with its tail at the center of gravity of the rod, which is the geometrical center, since the rod is uniform. So we can pretend that all the rod's mass is located here. For some purposes, that's a good approximation. Now we have a part of the rod that's immersed in the liquid. The liquid exerts a force on this part of the rod, the buoyancy force, which we know is vertically up, and we will show this force acting at the center of the part that's immersed, which is about here. Let's call the length of the immersed part of the rod x. The first thing that we will do here is write B in terms of W. By Archimedes' principle, B is the weight of liquid displaced by the immersed part of the rod. That's equal to the mass of the immersed part of the rod times G. What is the mass? Well, it's the density of the rod times the volume of the immersed part of the rod times G. Well, actually I should say it's the density of the liquid times the volume of the immersed part of the rod, because the volume of the liquid displaced is equal to the volume of the immersed part of the rod, and this is multiplied by G. The liquid has relative density 0.9, so its density is 0.9 times 1000, which is 900. Now, what about the volume of the immersed part of the rod? That's equal to the volume of the water displaced. How do we get its volume? Well, we could multiply its length, which we're calling x, by its cross-sectional area, which we will call A. Now later on we will derive a formula for getting B, but now we'll just attack this directly. So the rod is uniform, so the cross-sectional area is uniform, so we just need to multiply the length x by the cross-sectional area to get the volume of the immersed part of the rod. Okay, so that's density times area, and we multiply that by G. Now we've introduced a new letter that we don't want. We want to actually get rid of it. So to get rid of this A, well, we can get A in terms of W actually. We need to consider the weight of the entire rod. We can write the weight of the entire rod in terms of A, so then we can sub in for this A and get rid of A. We were given that the entire length of the rod is 2, so if we multiply 2 by the cross-sectional area, we'll have the volume. This is the volume of the rod, and if we multiply the volume by the density of the rod, we'll have the mass of the rod, and then multiply this by G to get the weight of the rod. We were given the relative density of the rod, 0.756, multiply this by 1000 to get the density of 756. Now we rearrange to get A because we want to eliminate A. So we have A in terms of W, and what we can do now is sub this in for A up here, so that we will get B in terms of W and in terms of X, the length of the immersed part. So simplifying here, 900 over 1512 is 25 over 42. So B is 25 over 42 times X times W. Now, when we finish this problem, I will derive a formula to get B for the general case of part of a rod immersed in a liquid. A formula to get B in terms of W, which will involve the density of the rod and the density of the liquid. Now, remember we want X, the length of the immersed part of the rod. So we use the fact that the rod is in equilibrium to consider the moments of the forces B and W. By equating the moments of these two forces about a point, we will be able to eliminate W and hence find X. Now the obvious point to take moments about is point P. That way we don't have to consider forces on the rod at point P. Forces on the rod at point P have zero distance to point P. Their moment about point P is 0, so we only have to consider these two forces. We can see that B acts to turn the rod in a clockwise rotation about point P, whereas W turns it in the other direction, anti-clockwise. So the moment due to B about point P must equal the moment due to W about point P. So we take the magnitude of B, which is 25 over 42 x times W, and multiply by the perpendicular distance of the line of action of B from point P. So here's the line of action of vector B, and this green line is the perpendicular distance to P. We got a pair of Z angles here. We can see that this green line is the side opposite theta in this right angle triangle. So we need to multiply the hypotenuse of the right angle triangle by the sine of theta to get the distance that we require. So what's the hypotenuse? The distance from here to here. Well, we will have to get this in terms of x. The distance from here to here is x over 2. Okay, it's half of x, because B acts at the midpoint of this segment. Actually, it's easier to consider this distance here. Okay, this is x over 2, and subtract this distance from the length of the rod, which is 2. So the hypotenuse, the distance from here to here, is the hypotenuse of this right angle triangle is 2 minus x over 2. So we multiply the hypotenuse, 2 minus x over 2, by the sine of theta. That will give us the perpendicular distance of P to the line of action of B. Okay, we see that B has a clockwise moment about P. W has an anti-clockwise moment. So we multiply the magnitude of W by the perpendicular distance of the line of action of W from point P. That's this distance here, which I'm showing in blue. Now we have a pair of Z angles here. These angles are the same. So we have to multiply the hypotenuse of this right angle triangle by the sine of theta. Well, W acts at the center of the rod, so this line here is half the length of the rod. Half of 2 is 1. So we multiply the hypotenuse 1 by the sine of theta to get the side opposite theta. 1 times sine theta is sine theta. Now notice that sine theta cancels on both sides. So that's good because we don't want any extra variables appearing. The W's cancel out. Okay, so that's why we got B in terms of W in the first place, so that when we go to take moments and equate the moments, you know, we can cancel common terms. W is a common term. And now you see we are just left with an equation in x. So we've divided the right hand side by W sine theta. That's going to give us 1. So we have 1 on the right hand side. On the left hand side we have 25 over 42 times x into 2 minus x over 2. And on the right hand side we have 1. See here, we're going to get a quadratic equation. X by x is x squared. Now we can multiply this equation by 42 to cancel the 42. So we have 25 by x by 2 is 50x. Then we have 25 by minus a half x, or minus 25 over 2. X squared, we have an x squared from this. 42 by 1 is 42. We can multiply everything by 2 here. So we get 100x minus 25x squared equals 84. Now, if you rearrange this into standard form and solve the quadratic equation, there are two answers. You get 2.8 or 1.2. Now, in the context of our problem, 2.8 is not a solution, because if we go back up here, we see that the rod is 2 meters long. So x, the distance from here to here, has to be less than 2. So x cannot equal 2.8. X can equal 1.2 though. X has to be less than 2. In the next part we want the value of theta. Well, if we go back up here, you see that we can form a right angle triangle that contains angle theta. And we have two of the sides of this right angle triangle. We are given this side here, and we know the distance from here to here now. The hypotenuse is just the length of the rod, which is 2, minus this distance, which is x. We've just worked out x. X is 1.2, so the hypotenuse is 2 minus 1.2 or 0.8 meters. So we use the fact that the cos of theta is the side adjacent to theta, 0.4, divided by the hypotenuse, 0.8. So the answer to part 2 is inverse cos of a half, or 60 degrees. Now, as I said earlier, I was going to look at a formula for B in terms of W. So this is the general case of a rod with density rho r, a uniform rod at that. So cross section is constant everywhere, and the density is uniform. And we have a liquid whose density is rho L. By Archimedes' principle, that the buoyancy B is the weight of liquid displaced by the immersed part of the rod. So what's the weight of the liquid displaced? Well, we have to get the density of the rod. Well, actually, we're dealing with the weight of liquid displaced, so we need the density of the liquid. We need to multiply that by the volume of the rod, the part that's immersed. So let's look at that. So the volume of liquid displaced is equal to the volume of just this part of the rod. So like before, we'll say that A is a cross-sectional area. So we multiply the cross-sectional area by x to get the volume. So we have the density of the water displaced multiplied by the volume of the water displaced, and we have to multiply by g. So we get the weight of water displaced. Next, just like before, we have to try and get rid of this A. So to do that, we bring in the weight of the rod. We want to get B in terms of W after all. So let's write down the weight of the rod using its volume and density. So what's the volume of the rod? Well, it's the cross-sectional area, A, multiplied by its length. Let's say the length is L, capital L, using small l for the liquid. Okay, so this is the volume, and we multiply this by the density of the rod. Volume times density gives us the mass of the rod, and we multiply by g for the weight of the rod. Next, we rearrange this for A, and we have to just plug this thing here in for A. So here is a formula that you could just memorize. You see, it involves the ratio of the part of the rod that's immersed to the total length of the rod. And it also involves this ratio of densities. The density of the liquid over the density of the rod. Okay, one way to help recall this formula is that the density of the liquid has to be on top, because we know that as the density of the liquid increases, the buoyancy force increases. Okay, the buoyancy force due to a more dense liquid. Well, the buoyancy force goes up as the density goes up. That kind of makes sense. We can imagine a more dense fluid being able to exert a greater force on an object immersed in that fluid. So that's one way to remember that rho L appears on top. The density of the liquid appears on top. By the way, notice that B is less than W. Now that makes sense for equilibrium. Okay, this rod is in equilibrium. So the magnitude of B, well, the reason the B has to be less is that the moment of B is greater than the moment of W, because B is further away from point P when we take moments about point P. Alright, so I need to show B as a vector with smaller magnitude than W, because we're multiplying the magnitude of B by the perpendicular distance of the line of action of B to P, and that's got to equal the magnitude of W by the perpendicular distance of the line of action of W to P, which is less. So you can see now why B has to have a smaller magnitude than W, and that's reflected in the formula. See, the density of the liquid will be less than the density of the rod. Okay, otherwise the rod won't actually become immersed in the liquid. Okay, we saw that in the previous video. So this number here is less than 1, because rho L is less than rho R, and this number is less than 1, because x, the immersed part of the rod, is obviously less than the total length of the rod. So we have two numbers less than 1 multiplied together. So everything in front of W is less than 1. So B is some fraction of W. In other words, B is smaller than W. Let's look at another example. A thin uniform rod PQ of weight W is in equilibrium in an inclined position with end P immersed in a container of water. The end Q is supported by a vertical force F, so F has no horizontal component. The relative density of the material of the rod is S. Find in terms of S the fraction of the length of the rod that is immersed. Okay, let's look at the part of the rod that's immersed. We have a buoyancy force on it. We'll put it acting at the centre of mass of the immersed part of the rod. The rod is uniform, so the centre of mass is just the midpoint of this line. So that's B. And we have the weight of the rod acting at the midpoint of the rod. Again, we're dealing with a uniform rod. So we get the midpoint of the line PQ, and that gives us W. Now W, as we just saw, actually has greater magnitude than B, because if we consider moments about point Q, the moment of W must equal the moment of B. But since W is closer to this point, then the moment of W is greater. Anyway, okay, let's look at B. I won't use a formula for B. I'll just do it the way I did the previous question. B, by Archimedes' principle, is the weight of liquid displaced by the immersed part of the rod. So we have to get the density of the liquid displaced. Actually, the density is the density of water, which is 1000. Multiply that by the volume of the liquid displaced. Well, the volume of the liquid displaced is equal to the volume of the immersed rod, which is the cross-sectional area of the rod A times the length of the immersed rod, which is X. Okay, so all we did there was got density times volume, giving us the mass of the displaced water. We get rid of A, as we saw before, by considering the weight of the rod. Let's suppose that the length of the rod is L. Well, one way to get the weight would be to get the volume of the rod, which is L times the cross-sectional area, that's the volume, multiply that by the density of the rod, rho r, that's the mass of the rod, and then multiply by G to get the weight of the rod. Now, we can use the fact that the relative density of the material of the rod is S. Okay, S is the relative density. If we multiply S by 1000, we get the actual density of the rod. So we have 1000 LAG. So we rearrange this formula to get A, and we plug this in up here. Nearly forgot the S here. Rho r is 1000 S. And we have G up here. So G's cancel, thousands cancel. Okay, next we consider moments. We take moments about the point Q. So that means that F has no moment about this point, because the line of action of F passes through the point Q. So only B and W have moments about Q. Well, they're the only other two forces acting on the rod. B has a clockwise moment about Q. W has an anti-clockwise moment about Q. And these moments must equal each other for equilibrium. So let's start with B. Well, we need to get the distance of B to the point Q before we can get the perpendicular distance of the point Q to the line of action of vector B. First, let's consider the distance of the part of the rod that's not immersed. Well, that's the total length of the rod, L, minus the length of the part that's immersed, which is X. Now we have to consider the distance from here to here. Well, that's half of X, or X over 2. So at last we can get this distance here. It's L minus X plus X over 2. Well, minus 1x plus a half X, that's minus a half X. So we get L minus half X, or L minus X over 2. So here is the moment due to B. We multiply vector B by this distance here. So how do we get this distance? Well, this is opposite this angle, which I'm calling theta. So we multiply the hypotenuse, L minus X over 2, by the sine of theta. So that's what we have here. And that must equal the moment due to W. So we have to get the perpendicular distance of the line of action of W from the point Q. So we want this distance here. So that will involve this angle in here, in this right angle triangle. Well, these angles are the same, they're corresponding angles. but we want the distance of W to the point Q. Well, that's just half the length of the rod. The weight is at the center of mass. That's just half of L over 2. Sorry, that's half of L, which is L over 2. Okay, so this blue distance here is L over 2, and we have to multiply L over 2 by the sine of theta to get this distance. So we're going to get the magnitude of W times L over 2 sine theta. Now we can plug in for B. We got B in terms of W. B is W over LS. So the factor of W appears on both sides, so that disappears. Again, that's the reason why we get B in terms of W. So that when we equate moments, the W's cancel out. The sine theta cancels out, so it doesn't actually matter about the size of this angle here. Disappears. A thin uniform rod PQ of weight W is in equilibrium in an inclined position with end P immersed in a container of water. The end Q is supported by a vertical force F, so F has no horizontal component. The relative density of the material of the rod is S. Find in terms of S the fraction of the length of the rod that is immersed. Let's suppose that the length of the rod is big L and the length of the part that's immersed is X. Okay, let's look at the forces on the rod. Well, we have F shown. The weight of the rod acts at the center of mass. Since the rod is uniform, the center of mass is the midpoint of the line PQ. We call it W, and that's what we're given here. Now, what about the buoyant force on the rod? Well, that's on the immersed part of the rod, and that acts at the center of the immersed part of the rod, which is about here. And we know that B actually has smaller magnitude than W, because B is further away from point Q, and both forces have to have the same moment about point Q. Okay, normally we start by getting B in terms of W. B, by Archimedes' principle, is the weight of liquid displaced by the immersed rod. Well, that's equal to the volume of the immersed rod times the density of the liquid displaced. Okay, the volume of the liquid displaced is equal to the volume of the immersed rod. So what's the volume of the immersed rod? Well, that's the length x by the cross-sectional area, which I'll call A. Okay, we saw this thing before. That's the volume of the immersed part of the rod, which in turn is equal to the volume of the water displaced by the immersed part of the rod. Then we want the density of the water. Well, that's 1000. So volume of displaced water by density of water is the mass of the displaced water. Multiply that by G to get the weight of the displaced water. Now, as we saw before, we need to get rid of A, so we bring in the weight of the rod W. We get the weight by getting the volume of the rod, which is the total length L. The total length is L times the cross-sectional area. That's the volume of the rod. We multiply that by the density of the rod. Okay, that gives us the mass of the rod, and we multiply by G to get the weight of the rod. Now, we are told that the relative density of the material of the rod is S. So S is the density of the rod divided by 1000. Or the density of the rod is 1000 times the relative density of the rod. Okay, relative density is the density of a substance relative to water. We divide the density by the density of water. So we can replace rho r here with 1000 S. So I'll write this as 1000 L A S G. So we rearrange to make A the subject of this, and we take this quantity here and plug it in for A over here, and that way we can get B in terms of W. So after the cancelling, we get XW over L times S. Now if we compared this to the formula that we derived earlier for the buoyancy, see, it makes sense. We have X over L just like here. Now we've rho L over rho R. Well, the liquid in our case is water, and the density of water is 1000. So this quantity here is actually 1000 divided by the density of the rod. But we know that the density of the rod divided by 1000 is S. So if we turn that upside down, 1000 over the density of the rod is 1 over S. So that explains this S underneath the line. So it's 1 over S times X over L times W. Next we will consider moments about the point Q. Point Q is convenient because the moment of F about the point Q is 0, since the line of action of F passes through the point Q. So to get the moment of B about the point Q, we take the magnitude of B, which is XW over L times S, and multiply by the perpendicular distance of the line of action of B from Q. Now to find that line of action, we need a distance from here to here. So this will be the hypotenuse of this right angle triangle. We multiply the hypotenuse by the sine of this angle here to get the side opposite theta. Okay, so to get this distance, we get the total length of the rod, which is L, and subtract this distance here. Now what is this distance? Well, the distance from here to here is X, and the buoyancy force is positioned at the midpoint of this distance. So distance from here to here is half of X, or X over 2. So the distance that we require is the length of the rod minus X over 2. It's L minus X over 2. So we have to take L minus X over 2 and multiply by the sine of angle theta. So that's the moment due to B. It's a clockwise moment, and for equilibrium that must equal the anti-clockwise moment due to W. So we take the magnitude of W and multiply by the perpendicular distance of the line of action of W to the point Q. So here's the line of action of W, and here's the distance that we require. To get that distance, we need to get this distance here. But W acts at the midpoint of the rod, it's positioned at the midpoint, so this distance is just half the length of the rod. That's L over 2. So we multiply W by L over 2, but we have to multiply L over 2 by the sine of this angle here. Now this angle here is the same as this angle here. These are corresponding angles. These two lines are vertical. So in this right angle triangle, L over 2 times sine of theta is the side opposite theta. Okay? These two angles are the same. Actually, it doesn't matter what angle theta is, because as you can see, these cancel out. So even though we're talking about the perpendicular distance of the line of action of the forces to the point Q, we could have just actually multiplied by the distances of the forces to the point Q, just the straight line distances. Okay, but in general, of course, we want the perpendicular distances of the line of action of the forces to the point. Notice also, of course, that W cancels out. That always happens. So that's the reason why we always want to get B in terms of W. So when we take moments, W disappears. Okay, now let's be clear about what we're after. We are not looking for X. We can't find X, a value for X, because we don't know anything about the rod. We don't know the length of the rod. We want a fraction of the length of the rod that is immersed. So we want the length of the immersed part, X, divided by the total length, L. This is what we're after, not X, X over L. Okay, if we multiply in here, we get X over S times L over L, that's X over S. Then we get minus X squared over 2 LS. Now, I'm going to multiply everything by 2ls, actually minus 2ls, so this term becomes plus x squared. See, we have an equation in x here. Actually, what would probably be a better idea is to get an equation in x over L. This is the quantity that we really want, the ratio of immersed length to total length. So how do we rearrange this thing? Well, we could multiply everything here by 1 over L. So we'll get an x over L here. Well, we have a 1 over s in front of it. Okay, if we multiply this by 1 over L. Get L goes in under the x, and L goes under the x squared here. I'll take out the minus 1 over 2s, and we'll have x over L squared, and on the right hand side we're going to get L over 2 times 1 over L. That's a half. Now of course you don't have to do it this way. We could have just got an equation in x, a quadratic in x, and solve it. Here I have a quadratic equation in x over L. So the solution is x over L equals minus b, that's the coefficient of x over L. It's minus 1 over s, or 1 over s, plus or minus the square root of b squared. That's minus 1 over s squared. Minus 1 over s times minus 1 over s is 1 over s squared. That's the b squared. Then minus 4 times a is 1 over 2s times c, which is a half. And the whole lot is divided by 2 times a. 2 times 1 over 2s is 1 over s. Okay, so we're solving, remember, for this quantity here. Okay, so we have a quadratic equation in this quantity. So a is this minus 1 is 1 over 2s, b is minus 1 over s, and c is a half. Okay, multiplying in here, we get some cancellation, not much. Now, to simplify this thing, it would be best to multiply above and below by s. So we multiply on top by s and multiply underneath by s. Okay, if we multiply on top by s, s times 1 over s gives us 1. So we plus or minus s into the square root of this thing here. Now we could actually take that s inside the square root sign. We take it inside the square root sign, it becomes s squared. Okay, because the square root of s squared is s. So we have the square root of s squared, which is s, times the square root of this here. Well, that's just the square root of s squared times what's inside, which is 1 over s squared minus 1 over s. And this is divided by 1 over s. 1. We've multiplied underneath by s. So multiplying s squared into this, we get 1 minus s squared over s, which is s. Now, x over L is a fraction that's less than 1. But it's also positive, of course. You know, x is a positive number, L is the length of the rod, they're both positive, so it's a number that's actually between 0 and 1. So if we go up here, we've a choice of solutions for x over L. We could have x 1 plus the square root of 1 minus s, or we could have 1 minus the square root of 1 minus s. Now the square root of 1 minus s is going to be some positive quantity. You know, because the sign of the square root is taken care of by the plus or minus. So one solution is a number that's greater than 1. Because we're adding something onto 1. So we have to disregard this, because our solution x over L has to be less than 1. So this must be the solution. By the way, notice as an aside what's inside the square root sign. S is the relative density of the rod, and that has to be less than the relative density of water. Okay, the relative density of water is 1. It's 1,000 divided by 1,000. So we need s to be less than 1. If 1 minus s is going to be greater than 0, we cannot get the square root of a negative value. Okay, if we want real solutions to our equation, we want x over L to be a real number. 1 minus s has to be positive, which means that s has to be less than 1. And that's the condition for the rod to float, actually. The relative density of something must be less than 1 if it is to float in water. Okay, the relative density of the floating object must be less than the relative density of the liquid. Or if you like, the density of the rod must be less than the density of the liquid, water in this case, which is 1,000. In part 2, we are given that if s is 3/4, find f in terms of w. So here's x over L. Let's plug 3/4 in to get the ratio of the immersed part of the rod to the total length of the rod. Well, we can see it's 1 minus the square root of 1/4. That's 1 minus a half, which is a half. Now we need to consider the forces acting on the rod. See, we need x over L to find out what B is. B is x W over L times S. So in our situation, X over L is a half. What about S? Well, we're given that S is 3/4. So we get W divided by 3 halves, which is 2/3 W. Okay, so we've this force of magnitude 2/3 W acting vertically up. We've a force of magnitude W acting vertically down. The rod is in equilibrium. Now, since these two forces are both vertical forces, this force at F must be vertical. Actually, we needn't have been told that force is vertical. We know that these two forces are vertical. So for equilibrium, none of the forces acting on the rod must have horizontal components. So, by Newton's second law, the resultant force in this rod is 0, or the sum of the forces pointing upwards, so F is one of them, plus 2/3 W, must equal the sum of the forces pointing downwards. So we see that F is 1 W minus 2/3 W. That's 1/3 W, or W divided by 3.